I don't know why it does that, but there it is. All right, so the first part, the first error you'll see here is that this is not a channel. This is an ATPase pump. So I hear you talking. When I move you, don't get upset. Don't tell me I'm not doing anything. ATPase. Oh. ATPase pump. So I hope that in your mind you see, instead of a channel, which is just an opening, this is actually moving things, actively moving things from one side to the other. So when you see that word pump, I hope you're thinking active movement, like pumping an air tire, right? Or pumping water. You actually have movement. All right. The next error that I have here is that this, I'm going to talk about in a minute, this should be going upwards, not downwards. So this is the leaky channel is actually moving ions out. And here, the leaky channels are moving ions in. Which ions? Specifically, here it's moving potassium into the cell. Here it's moving sodium out of the cell. Okay? Change the arrow directions. And then don't get rid of this where it says in, where it says into the cell. Get rid of that. What it should say is out of the cell. So it's moving potassium out of the cell. It's moving potassium, or K plus, out of the cell. K plus is potassium ion, out of the cell. Where Na is sodium, it's moving sodium into the cell. So make sure you have that straight in your mind. And you have it straight in your notes. So those are two mistakes I made here. One more mistake I made, which is I left something out. It's a mistake of omission. There should be a 6 protein, which I did not write here. And that 6 protein should be voltage gated channel. Voltage gated channel. So 6 proteins. Yes. We have the pass back. So there's 6 proteins. One of them is this sodium potassium ATPase pump. That's the one we're going to be talking about first. Another one is a potassium ion channel. It's called a leaky channel. Another one's a sodium leaky channel. Then there's a ligand, and then there's a pressure applied, and then the voltage gated channel. So let's talk about each one appropriately before we move on. We're going to use all 6 of these, to explain a nerve, how a nerve works. How does your neuron work? First thing you should know is that this pump is an enzyme. That's why it says ACE here at the end of it. The second thing is that this binds 2 potassium ions. Here there's space for 3 sodium ions. This pump is going to move 3 sodium ions out while moving 2 potassium ions in. And it's going to use ATP. The reason it's using ATP is because this is active transport. This is moving against the concentration gradient. You should be adding to your notes at this point. This is moving against the concentration gradient, not with it. So sodium is moving, it's moving sodium out because over here, sodium is higher, and this is moving sodium out. So it's going from low to high. When things move to low to high, that's because Or when you move things from low to high, you need to use ATP. ATP is the energy source for your cells. Potassium is getting moved in. Potassium's high inside, low outside, so it's moving from low to high. Again, you need that ATP to move this against the concentration gradient. These two are leaky channels. These are actual channels, not pumps. There's no energy required because this is passive diffusion. So this was moving potassium in. You need ATP to do that. But here, this was allowing potassium to go out. So potassium ion goes out. It's called facilitated diffusion. It's passive. It has no extra energy required, no ATP required. This is sodium ion. It's a sodium ion channel. Again, it's leaky, meaning it's going to go from high to low. So notice that here, to move it from low to high, you need ATP. Here, no ATP is necessary. It's just going to allow sodium to leave. Now, this is a key point that you need to make sure you write, you underline, highlight, whatever it is you got to know to learn it. There's more potassium leaky ion channels than there are sodium. Much, much more. The membrane allows potassium ions out much easier than allows sodium ions in. That's incredibly important for the rest of this discussion. More, that's right. It says it right there. Many more potassium ions are let out than sodium is allowed in. Many more leaky channels in the membrane for potassium than there are for sodium. So make sure you know that as we go on and discuss this. So we call it a leaky channel because it literally leaks. Like it's just a hole that allows potassium out. This is a hole that allows potassium in or sodium in. And it does that just from concentration gradient, highest to low, high to low. Yeah.
Okay. I was gonna ask if I go to the bathroom. I'm gonna ask when I come back to the bathroom.
All right, go. Yeah. No question. I thought you had a question. All right. This one here is called a ligand-gated channel. And that's where a ligand binds to the protein. Ligand is a molecule. It's just a molecule that binds to a protein and changes its shape. So it's something that binds to the protein and changes its shape. Has anyone here done the case study at all or started it? Some people have. Do you remember reading about what ligand would be involved in binding to a protein in a neuron that would make it open a channel? What is it? What do they call it? It's not quite a hormone, no, but it's something else. Do you have any examples in your mind? Do you remember the one serotonin, maybe dopamine, GABA? You have never remember reading or listening or hearing any of those in the case study? Yeah, the one I signed on Monday. Today's Wednesday, by the way, so it's not quite just assigned. Yeah, the one I signed on Monday. So those are called neurotransmitters. Neurotransmitters. And neurotransmitters are ligands. They are... I literally just spent like 10 minutes talking about wearing hoods in the building. Thank you. So the ligand is, the neurotransmitter is a ligand because it binds to the protein, it opens a channel. So the ligand acts like a key to a lock, where the protein is the lock. That when the key binds to the protein, the lock opens, the ions flow. Is that clear? Does that make sense? So that's a ligand-gated channel. And then there's the voltage-gated channel. Now, to understand voltage-gated, you have to understand what a volt is. And to understand that, we have to say that a volt is a measurement, is a unit of charge, electrical energy, electrical charge. A unit of electrical charge separation. So when you look at a battery, and you look at this kind of, you've seen these batteries before. They're kind of rectangular batteries. You've seen them, yes? It's like this is a 9-volt battery. What that means is that there's 9 units of separation between the positive and the negative.
So what about watts?
Watts is a measurement of power, electrical power.
Okay.
This is a measurement of electrical separation of charge. So 9 units of separation between positives and negatives. The negative is called an anode, and the positive is called a cathode. You should have learned this in middle school, but that's fine if you didn't. You're learning it now. So that's a basic battery. It's a 9-volt. The AAA work the same way. The AA work the same way. They have a little positive side, the cathode, and the negative side is the anode. Your watch batteries look like this. They also have a positive and a negative side. They're kind of like little pills. Your battery in your phone looks something like this. It's real thin. I don't know how many volts that is. I have no idea. But it also has a positive and negative side to it, and there's a separation of charges.
What's that word underline?
Cathode, and anode. Anode is the negative, cathode is the positive. All batteries work the same way. Your cells can act as batteries. They can separate charges. That's what your neurons do. You're using electricity to run your brain. So when you're thinking, you're using electricity. So can I go on, or do we need more time? What do you guys think? All right. You'll see here I wrote the summary of the notes already. The membrane is more permeable to potassium than sodium. Why do I say it's more permeable to potassium than sodium? Because there's more leaky channels for potassium than there is for sodium, which is what I said. The net result is that all the interactions of the action potential. So the result of all 6 of these is the action potentials. Your thought, your movement is the result of these 6 proteins working together. A signal is sent from one cell to another cell, allows you to do what you do. Can I go on? No, I don't hear any no's. There are a couple people yes. Yes. So, what is volts? Let me talk a little bit really clearly here what a volt is. When you have what are those square batteries? You've seen these rectangular batteries before, have you not? They have like a little things like this, and one side's positive and the other side's negative. You've seen that battery before? This is a 9-volt battery. What that means is that this volt, V means volt, and volt is a unit measuring the difference in electrical charge between, well, you don't have to, it's not going to be on any test, but if you don't understand it, it's going to confuse you later. Between 2 sides. Every battery has 2 sides, has a positive and a negative. The positive known as a cathode, and the negative is known as an anode. You should have covered this in middle school, or you should cover it in physics or physical science. But whether you did or not, that's something you deal with every day. You buy batteries all the time. You should have some idea what's going on. Car batteries, 12 volts. This battery is a 9-volt battery. The AAA is smaller, AA is smaller, AAA is even smaller. The watch battery is even tinier. Lithium ion works the same way, just uses a different kind of ion. So anyways, That's what volt means. The difference, please think about this because I'm about to talk about it. The difference in electrical charge between two sides, we measure that in volts. Volts. Now that's fine for us for a battery, but we need a cell is really tiny, so we can't use volts, but we can use millivolts. So we can measure the difference in electrical charge on two sides with something called millivolts, whose units go MV. That means that 1,000th, right, of a volt. A very tiny amount of current, or not current, difference in charge. We call this, another word for this is electrical potential. The potential to allow current to happen is called electrical potential. So you have a lot of positives. Here you don't have so many positives. If you open up a channel, you get flow of ions. We call that electricity. That's what electricity is. When you plug in a phone, you're getting the movement of ions. That's it. Movement of electrical charges. It's usually electrons through a volt like that, but through a regular battery, but there you have it. We can actually stick an electrode, and what happens is, what's interesting is that this side, the inside of a cell is negative 70 millivolts, which means, if you think about the definition of what millivolts means, that means that this side is 70 times more negative. 70 times more negative than the outside. That's what that means. That's what that negative 70 millivolts means, is 70 times more negative than the outside. That means there could be flow, but you need to have a channel to allow the flow to happen, but that means there could be flow. Are we good with that? Does anybody have any questions about it? I mean, it's a lot, but... Negative 70 millivolts means it's 70 times more negative inside than it is outside. That's what that means. You see how the electrodes on the inside? You see a little doodad is sitting inside the cell? That's measuring the difference between inside the cell here and outside over here. Look, see how you have one end is outside, the other end is inside? It's looking to see what is the difference in charge. And they're saying negative 70. So it's 70 times more negative on the inside. So to summarize all this, on this slide, I wrote out the main ideas here for you already. It's already written. It's in front of you, so you don't have to write it or take pictures of it. I thought it would help you. When one side of the membrane has more positive ions than the other, there's a potential for current. This is called voltage. The membrane is said to be polarized. So this membrane is polarized because you have more positive outside than you do have inside. The level of polarization is measured in millivolts. A nerve cell is at rest is about negative 70 millivolts as measured from the inside compared to the outside. Now, I ask again, did that make sense? I see people nodding. I see no questions or hands up. Okay, I'm going to move on. You know it. Now, this goes through the specifics of the sodium-potassium pump. So let's go ahead and take a look at the first step. The pump starts off this way, with the inside being open to 3 places where sodium combined. These sodium ions combine to these places, 1, 2, and 3. They go in and they bind. This is a membrane spanning protein. It has to go all the way across. I hope you realize that, because if it didn't go all the way across, it couldn't do its job. So outside the cell, as we said earlier, there's more sodium than there is potassium. So sodium is high outside, potassium is low. Inside, potassium is high and sodium is low. So we're going, for sodium, we're moving from low to high. I hope you see that. So you need something, you need ATP if you're going to do that. So here is the next step. ATP comes in, binds, that allows the sodium to bind and close. This protein changes its shape. It's changing its shape. That means it's changing its conformation. The word for changing shape in biology and biochemistry is conformation. Its shape is changing. So it went from that open look that you see in number 1 to this closed, the sodium is trapped inside here in number 2. Then out comes the ADP. It used to be ATP, adenosine with 3 phosphates, but now it's ADP, adenosine with 2 phosphates. This is the chemical energy of the cell. The energy uses this, the cell uses this form of energy, ATP, to do stuff, to do work. In order to do work in the cell, you need ATP. That's going to be, you need to know that for sure. I'm going to ask it on tomorrow's quiz. In order to do work, you need ATP. There'll probably be about 5 to 10 questions on tomorrow's quiz. You need to know that. So as you see in the first, you have the sodium, it's open, it has 3 spots for sodium. There's sodium inside, sodium goes in, ATP binds, out comes ADP. The sodium is bound and trapped in the protein. The protein changes shape and traps the sodium. Now in the third step, what you have is a phosphate that came off the ATP is still stuck here. That changed the shape of the protein. That allowed the sodium to leave. Because you see now that's open to the outside. And the inside, in comes 2 potassiums. Because this has a spot for 2 potassium. Notice I color-coded it for you, hoping that it helps. The pump releases the sodium, accepts the potassium. I also wrote down all this information for you already. The pump releases the sodium, accepts the potassium. The binding of the potassium changes the shape or conformation of the protein. That should say protein. You might want to write that in. That should say protein. Let me go ahead and add to that and say protein. So the changes the shape of the protein, which allows that to happen. Number 4, when the potassium binds and you have a phosphate, the protein changes shape again. This is in the middle of that change of shape. And here you have, once it opens up to the inside, the potassium leaves. That knocks off the phosphate, and the protein's back to its original shape. It's ready to do it again. And it keeps doing it over and over and over again. That's what we call a pump. Right? That's the basic way ATP, the sodium potassium ATPase pump works. You have to know that for tomorrow. So what do you need to know? You need to know the six proteins involved in this process. You need ATP in order to do work. You need ATP to do any cellular work. That's right. That's the other thing you have to know. And then you have to know how the sodium ATPase pump works. Those are your 10 questions on tomorrow's test. Quiz. You want to write that down? You want me to write it down? I really don't want to, because some of you are not you. Don't even get it. I can see the attitude starting in your face. Don't even, come, bring it down. Bring it down. Behind you, I can see people weren't paying attention. So, all right. So, let's go ahead and write that down. So one, you need to know quiz tomorrow. You need to know your 6 proteins. 2, and what, how they work in general. Next, you need to know that ATP is necessary for cellular work. And 3, how it specifically does sodium, potassium, ATPase work. I just explained it to you. You have the drawing there with the written notes already done for you. So those are going to be 10 questions on that. Multiple choice on Schoology. A different set for every class.
Does that say pace?
ATPase. So it's adenosine triphosphate, and ACE means it's an enzyme. So let me go ahead and change that to capital. You had a question, somebody? Yeah, give me a second.
Is that some tissue?
No, but you can go to restroom. ATP ACE. Zoom in where? Is that good?
For the potassium ion channels, was the potassium going out a form of what's it called?
Passive transport, also facilitate diffusion.
Exocytosis, yeah.
Not quite exocytosis, because exocytosis is when it is exiting the cell, yes. Okay? So that much. But usually exocytosis, you're talking about membranes, a lot, big things or a lot of stuff leaving very quickly. It's usually proteins. In fact, you'll see an example of that. There's an example of that in the cell, in the notes. I'm going to show you in a minute. Are we all good with this? Can I go on? Okay. Why I want to? Oh, I see. All right. So, what are some of the summaries of the stuff that we just talked about? Sodium potassium ATPase pump is an example of active transport. This is an example of active transport. It helps maintain the concentration gradient so that we keep the positive outside and the negative inside. How does it, you guys keep talking back there about nonsense instead of focusing on what's on the board? I'm gonna have to move some of you around back there. All right, I don't want to. I'd rather focus on actually teaching. This concentration gradient increases sodium outside and potassium inside. It keeps the outside more positive and the inside more negative. Is it almost time to leave? How many minutes? Oh, 10, 15, excellent. Well, if I lined a bunch of these books up in a row, and I did this, what would happen? It'd all fall down in a chain, right? It wouldn't fall down at once. This would fall, the next one, like dominoes. We call them domino effect, right? It's a chain reaction. Everybody understand that? All right. So when we talk about this concentration gradient being kept, we need the ability to have a high on one side and a low on the other, to be able to get things to happen. We're not going to be able to get the chain reaction to occur if we don't have a high and a low. So we need that electrical potential. There's two differences here. So this ATPase pump is pushing sodium out, is bringing potassium in. Give me your phone. Give me your phone. If I see a phone, what did I say I was going to do? So bring me your phones. Both of you. I saw both your phones. Bring me your phones. Just here. So we said sodium's getting pushed out, and potassium's getting pulled in, correct? We said that, didn't we? Look at your notes. It says in your notes, I wrote it. So that's what this pump is doing. That's what this pump is doing. It's pulling potassium in, is pushing sodium out. Correct? It's creating a high and a low chemical gradient, right? Because you have the chemical potassium is high inside, the chemical sodium is high outside, correct?
Yeah.
So that's a high and a low. That's a concentration gradient for chemicals. So that's a chemical concentration gradient. But because of the number of protons that you're moving one way or the other, there's also an electrical gradient. In other words, there's a positive side and a negative side. Does that make sense to you? That's called an electrical gradient. Together we call it the electrochemical gradient. Electrochemical gradient. The two together are an electrochemical gradient. Electrochemical gradient. So, there are consequences to this. If I have this ion channel, I have this membrane, I have this leaky channel. This is one of the channels that you have to know by tomorrow. There's this protein that sits in this membrane. It's leaky. It's always open. It's always open. That's why it's leaky. Potassium. This is the leaky potassium channel. It's a true channel because it just allows things through. Allows diffusion to happen. And you have potassium on one side, high potassium on one side, and low potassium on the other. In which ways is potassium going to flow? So now let's take a look. Those of you that can't see, look on the board and tell me if you have high potassium in here and low potassium out there, and this is a channel that lets things flow, in what directions is potassium going to flow? It will go in and out, but net movements which way? High on this side, low on this side, and what is going to happen? Are you confusing this with this protein? Yeah, this one. Okay. So we talked about a minute ago about a membrane protein that required ATP. Did we not?
We did.
We did. Yes, we did. In case you're wondering, we did. That protein, I'm not going to draw all the things. It allowed potassium to come in and allowed sodium to go out.
That's why I said it's going in.
Right, I know that's why I understand why you said that. I understand why you said that. But I need you to understand that I wasn't talking about this protein. So this is called an ATPase pump. Sodium, potassium, ATPase pump. You're absolutely right. That's exactly what would happen. Potassium would come in, sodium would go out. You're right. That's correct. But the reason that happens is because ATP is being used. ATP goes to ADP. This creates a high sodium outside. How come there's high sodium outside? Because it's taking 3 sodiums and moving it out all the time. Does that make sense? It's pumping it out. This is also taking 2 potassiums and moving it in. So guess what? There's a high potassium in here. But because of that, now that's what this is creating, the highs and the lows. Is that understood? That's this thing, the ATPase pump. But now let's look at this one over here, the thing called the leaky channel. It's leaky. This is passive transport. There's no ATP. Do you see any ATP being used? No, good. So I knew why you made the mistake. It's understandable, but I need you to think about this, okay? Look at the difference. This is a leaky channel. This is another one of the proteins, not the sodium-potassium pump. Don't be surprised if this is the question that comes on the quiz tomorrow since we spent so much time on it. In which directions is the potassium going to go? Out. From high to low. All right. So we will continue this tomorrow after the quiz. So your electrochemical gradient on both sides has a high potassium on this side, low potassium on this side. For both. What's creating that electrochemical gradient, what's creating that high potassium is this sodium and potassium. Sodium, remember, is Na+, potassium is K+. Sodium-potassium pump that's pumping sodium out and potassium in, keeping the inside high. Now that's happening on the same membrane. So this is pushing the potassium in, pushing the sodium out. Well, this is a leaky channel, so the potassium is able to leak right back out along with this leaky channel, allowing the potassium to flow out. So that's two different proteins on the same membrane. This one, they're both working with potassium. Number 2 is the ATPase pump, and this one is working with both potassium and sodium. The first is a leaky channel. It's open all the time. This one, the pump, is only working when ATP is being turned into ADP, and that phosphate's being used to change the shape of the protein, allowing the sodium out and the potassium in. We just saw it. We went through it. You can rewind this and look at it if you like. But this one, in the leaky channel, the potassium is leaving. Why is it leaving? Because it's high. The concentration of potassium is high on this side and low on the other. It's high on this side and low on the other. So things are going to move passively. It's going to move through diffusion out of the cell. Remembering that this is out and this is in the cell. So that's due to the chemical gradient, right? The gradient, the concentration of potassium. The concentration of potassium on this side versus the concentration of potassium outside. But then there's another gradient. There's this gradient of overall charge that on the outside is more positive. I believe I've said that several times now. On the outside, the outside of the membrane is more positive. So let's just put a big plus sign here. And on the inside, it's more negative. And I believe I gave you in the notes and in class, I gave you a number for that. This is more negative. So this is positive and this is more negative. By how much? By this side is negative 70 millivolts. That's the difference between the inside and the outside. The inside is negative 70. So the question that I was trying to get to is that the concentration gradient of the chemical gradient is allowing the potassium to go out. What's this negative doing on this potassium? It's pulling it back in. So these two forces, as the concentration of potassium is saying it needs to leave, it's leaving, it's moving out, where the charge, the overall charge on the inside of the membrane is negative, it's pulling on the potassium. So there's two directions. That potassium ion when you're looking at a membrane, that potassium ion, that K plus, is sitting there. And if this is inside and this is out, it's being pushed in this direction because of the chemical gradient. And it's being pulled in the opposite direction because of the electro gradient. The difference in charges, the negative charge. So it's the balance between the equilibrium between that push and that pull, those two forces pulling, that that creates this balance. That balance being at negative 70 millivolts. That's the stable. That's what we call. That's going to be the resting potential. The resting potential is negative 70. Okay. So we're going to talk now about how all this gets put together. So let's refresh here. We got one protein, the sodium potassium pump. Sodium again, Na plus, potassium, K plus, pump. And I should put ATPase. Is pushing against the concentration gradient. Sodium is going out of the cell. Potassium is going into the cell. So that's happening. Then you have, we talked about the leaky channels nearby. You have the sodium leaky, and the potassium leaky channels. The sodium is leaking sodium into the cell, and the potassium is leaking potassium out of cell, because these are following the concentration gradient. So I'm going to go ahead and draw it one more time here just to make sure I'm being clear. So here's your membrane. We know this is negative 70 millivolts as compared to the other side at rest. We know that there's an ion channel. We know there's a leaky potassium, there's a sodium potassium pump, and then there's a leaky sodium pump, right? So there's three different proteins happen around here, around this membrane. We know that the leaky, we know that this is negative 70. In part, we know it's negative 70 because this is high sodium out here and low potassium out here. And we know that over here on this side, it's high potassium and low sodium. Again, sodium being Na plus. All right, so we know that since this is going to be the potassium channel in blue, we know that the potassium, and let me just keep the potassium at green like we were doing in the previous color code. The potassium is going to stay green because that's the So if you're going from high to low, this is a leaky channel. Again, leaky channel, potassium leaky channel, potassium ion leaky channel. Meaning it's going to allow the ions to leak through. It's not pushing anything. Then the ions are going to flow. Potassium go from high to low, and it's going to go in that direction. Now, right next to it, you have a sodium-potassium pump, which again, I'm not going to go ahead and draw all the spaces like I did with the other drawing. Here's a sodium-potassium pump. And here, this is going to use ATP. And why is it using ATP? I keep trying to say this. But it's using ATP it's using ATP because it needs the energy to push the ions against the concentration gradient. Remember, if it's pushing potassium, it's not going to go from high to low because it wouldn't need ATP for that. It's going to go from low to high. And if it's pushing sodium, it's not going to go from high to low. It's going to go from low to high because it needs it. That's why it's using ATP, okay? So if we look at those two, if we look at potassium, it's going to bring potassium from low to high. So it's bringing potassium in. Potassium is going in because of this pump. And the other one, the sodium, is being pushed out, again, from low to high. So this sodium potassium pump is doing both. So now the other leaky channel, the other leaky channel, remember this is the concentration on this side of the membrane, on the inside. Let me erase this because this has to be somewhat confusing for somebody. So let me just say this. Here the potassium is moving out. It's following the concentration gradient, which is high to low. And remember that this is the leaky channel for potassium. And remembering that the concentration of sodium on this side is low sodium, and that the potassium on this side is high potassium. That's the concentration on this side. The concentration on that side is this. So that explains why this goes through. It goes from high to low. This is simple diffusion. This is facilitated diffusion. This is going from high to low. That's why we call it leaky. This is a pump. This is all happening at the same time. This is pumping the sodium into the high. This is pumping into the lows. That's why it needs ATP. It needs energy. This is the form of chemical energy it gets. And here, this last one is sodium. And sodium is going to go from high to low. Sodium is going to go from high to low in this leaky channel. And why is sodium going to high low? Because it's also, again, this is a leaky channel. It's just a channel. It's not a pump. So this is where this is the potassium leaky channel. This one is the sodium leaky channel. Allowing sodium to leak back. This is creating the high on this side of sodium and the high on this side for potassium because it's pushing potassium this way. It's pushing sodium that way. It's using the energy from ATP to do that. These are letting the sodium and the potassium flow through. There's a lot more of these than you have these. There's a lot more potassium channels than you have sodium leaky channels. So what does that mean when you think about it? When you think about it, they have this membrane, there's all this leaking of potassium going through, going in this direction. There's a little bit of leaking in this direction of sodium. Okay? So there's some sodium coming in, a lot of potassium going out. So over here on this side, you have high sodium, but only a little bit is going in. Here you have high potassium, but a lot is going through, leaking out of the cell membrane. That helps make this side of the membrane negative 70 millivolts. It helps it make it more negative because you're getting a lot of this leakage in the opposite direction, moving from this high to low. It's moving in that direction. This sodium ion pump keeps working, keeps pushing, keeps creating the gradient. But all of this is trying to do is keep this homeostasis, this negative 70 millivolts. That's what it's trying to do. It's called the resting potential. We'll get back to this in the next slide. But the other ion channel that we have to look at is this voltage-gated channel. Now, there's a voltage-gated channel that allows sodium into the cell, and we'll look at that in a little bit. And then there's a voltage-gated channel that lets calcium into the cell. So and then there's a ligand channel. So here's the ligand channel. The ligand binds to the protein. When that ligand, and it's called a neurotransmitter, if you've been doing your case study and you've been thinking about it, it's called the neurotransmitter. Some neurotransmitters are dopamine, GABA. All right. There's others, acetylcholine, there's a number of them. So as this neurotransmitter, it's also known as a ligand. These are ligands, L-I-G-A-N-D. As the ligand binds to the protein, it opens up the protein, letting the sodium flow in. So now you get this big change in polarity. Now you're getting a lot of that sodium flowing in. Now you have a lot of sodium coming in, making this negative 70 become less negative. This negative 70 becomes less negative, more positive. When that happens, you've depolarized the membrane. You're creating charge. Flow of ions is creating a charge. This is becoming less negative. This is becoming less positive. It's becoming more and more equilibrium. This side's becoming more and more positive. As that happens, it's called depolarization. That depolarization changes the voltage. Right? You don't have as big a difference. It's not as close to negative 70 as it used to be. So because of that, these channels, another set of channels that react to the voltage, open. And when that happens, calcium in this case rushes in. As calcium rushes in, these vesicles that hold the neurotransmitter for the next cell, at the end of the cell, these neurotransmitters are created. They're inside vesicles. They're sitting there waiting to be released. This calcium influx binds to the vesicles. It forces them to release into this synaptic gap. Into the gap here that we had discussed earlier, I think 2 days ago on Monday. You see that these neurotransmitters, these ligands, go and reach the next set of proteins. They bind and open the next set of channels, allowing, again, sodium to flow through, that open up more voltage-gated channels that start this series of dominoes of falling. So one channel opens up the next channel, which opens up the next channel, and it sends a signal flowing down the axon, down the cell to the next cell. So this is a chain reaction. It starts with a stimulus. So the whole thing starts with a stimulus. Something sets it off. It could be pressure, like we said earlier on one of the other proteins in the membrane. You could have a protein in the cell membrane that reacts to pressure. And as something pushes down on that part of the protein, this protein opens up. So the pressure opens up this protein and allows ions to flow through. That change in voltage because of that then sets off the next kind of protein, the voltage gated channels, which turns on the next set of voltage gated channels, etc., all the way down like dominoes falling in a row. Ultimately, it gets to the end of this cell and the beginning of the next cell. It has to cross this gap, this space. And the way it does is calcium is let in. This is calcium ion. Gets let in through these voltage-gated channels. The change in voltage and potential across this membrane, the change in volts, the inside becoming more positive, the outside becoming more negative, allows the calcium to rush in. And that makes the vesicle fuse to this other membrane. And this in turn releases this neurotransmitter into the gap, which then binds to the next one, and it keeps going. So the signal is sent from one cell in your brain to your spinal cord, to another cell in your spinal cord, to another cell that's on your muscle, and then that muscle then sends signals through calcium changes, etc., to contract, and you have a flinch or you have a muscle movement. Voluntary or involuntary, doesn't matter. It's not the point. The point is that that's the chain of reactions that happen, the chain of events that occur to get a signal to go from one part of your brain to another part of your brain. So you have voltage gated channels that allow calcium in, that tell the vesicles that are holding the neurotransmitter to release the neurotransmitter. We call that exocytosis. I'm sorry, we're taking the dogs to the vet, so they're in the back breathing heavy. There's nothing I can do about it. It's why I'm absent today. That's all I can do. I'm just tired. I'm sick, and I had to take the dogs to the vet. There's nothing else I can do. I need to rest at home. All right. So then we have vesicle fuses to the membrane. The vesicle's membrane becomes part of this membrane. Out comes the neurotransmitter. That neurotransmitter, remember, is the ligand that binds to the protein. This is a ligand-gated channel that opens when the neurotransmitter attaches. And if you've done your case study on ecstasy, then you know that often some drugs work with mimicking the neurotransmitter, so they bond to the ligand. They'll replace the ligand and open this channel. Some drugs take the place of the neurotransmitter as they go back into the cell and push the neurotransmitters out, more neurotransmitters out into this gap, keeping this channel going, this signal going. And if these signals are in the pleasure centers of your brain, then you become addicted. So that's the basic way that addiction happens. Now, chemical interactions work to relieve pain or to increase pain in the case of some drugs. Well, some chemicals. The nerve cell receives signals in the form of neurotransmitters from the neurons. Once enough channels open on one end, the change in voltage sends a chain reaction down the axon. So it goes from neurotransmitter to open ion channels to depolarization of the membrane to more channels open. How did you depolarize the membrane? The open ion channels change the polarity or the voltage on the membrane, which is what we call depolarization or discharge, right? Like your phone being discharging as you're using it. The ions moving across the membrane discharges the electrical potential, or it depolarizes the membrane, and the more channels open, then that signal continues down the axon, so the axon is very long, and opens the calcium ion channels at the end of the axon, and those calcium ion channels signal the vesicles diffuse. Those neurotransmitters, which are ligands, cross the gap, attach to ligand ion channels, ligand-gated channels. They open up and they allow, again, ions through, which discharges the next membrane, and so on. The concentration gradient, which is required to keep the signal going, is reestablished by the sodium-potassium pump. All right, so let's take a look at this action potential. You've seen this before on video, in movies and in hospital shows, where you have the membrane, the little beep, and then you'll see the little machine go. It's so hard to draw in the car. So it goes and it goes beep. And then you see the next one and the next one. Every one of these is called an action potential. And this graph means something. And it means a certain set of channels are opening or closing. Just like we've been talking about. So we have these keywords here, where I'm going to talk about all of them, and they're all embedded in this chart. The whole thing is going to be found here at this video. Go ahead and watch this video. It explains everything I've been talking about. It's in 15 minutes long, but it's really dense without a lot of explanations, which is fine. But I know my explanations are longer, but I'm hoping they're a little more understandable. But whichever one helps you most, use that to understand what's going on here. So at the resting potential, like we talked about earlier, we're at equilibrium. So let me draw the membrane. Let me do it in yellow like I've been doing throughout this whole process. So you have a membrane. At resting potential, then the inside is at negative 40 volts versus the outside. So that's the resting potential. So when you have equilibrium, the leaky channels allowing sodium and potassium to go down their concentration gradients from high to low are balanced with the sodium-potassium ATPase pump, and everything's being kept at negative 70 volts. Now, something happens. Maybe something pushes on your pressure-gated channels, and but it's just a light touch. So you get maybe just a few of your pressure-gated channels being pushed, so you don't really get enough to get to the threshold. The threshold value where you get the action potential going, then where you get enough ions to flow through the membrane that you change this potential significantly enough that the voltage gated channels all open, is negative 55. So then maybe it takes 50 or 100 of these proteins to be set off, whatever it is. Once you reach that threshold, it's gone. You're gonna get the chain reaction. The chain reaction happens. One goes to one voltage gated channel changes to another, changes to another, changes to another, changes to another, impacts the next, impacts the next, and the action potential starts. Depolarization occurs, and enough depolarization occurs, it starts the next action potential down the line. So at this point, the ions are flowing and they're depolarized. The membrane is becoming more and more positive. Now, why is the membrane becoming more and more positive? Remember, the potassium channels are allowing potassium to go from, at this point, what's happening is the voltage gated channels opened up. And sodium is rushing in. a lot of sodium is rushing in. Usually, remember, it's high on this side. Sodium is high on the outside and low on the inside. And because of that, enough of these voltage gated channels were opened up because of the small changes in volts due to the pressure or whatever sensory apparatus set it off, whatever the stimulus was. Let's say pressure. There was enough pressure where the proteins opened up and changed enough voltage that the voltage gated channel started opening, and a massive release of sodium rushes into the cell. That changes this from -70 all the way up to +30. So now there's a real, but at some point, these voltage gated channels, they close up. They become inactivated. So now the channel is no longer allowing sodium to flow. But remember, the potassium is still leaving. And the sodium potassium through the leaky channels, more than sodium is coming in, more potassium is leaving. So a lot of pluses are leaving. And you have the ATPase pump pumping potassium, bringing potassium in, but sending a lot of sodium out, 3 sodiums for every 2 potassium. So that's happening. And because of the potassium channels, they're leaking, and you have the sodium potassium pump pumping, this side of the potential becomes more and more negative. And this potassium channels are slow to close, so they keep pumping, they keep flowing potassium out until this actually becomes hyperpolarized. It becomes more negative than normal. But eventually they close. They slow down. And so you have the sodium potassium pump pumping and bringing everything back into equilibrium. All right. So we have this really beautiful system where you get the ions opening because of some stimulus, pressure on your skin, pressure on the nerve. Start at -70 because of the balance of ions on both sides. It gets up to -55. It opens the voltage gated channels that take off and they depolarize the membrane. At some point they become inactivated, and these all start to and then the sodium, all the potassium channels and the sodium potassium pumps bring the membrane potential back down, so often way too lower than they would have liked. And then the sodium potassium pump finally brings it back up to equilibrium. So that is the meaning of this action potential. So this is called depolarization because it's becoming less. This is becoming less negative. It's becoming less polar, right? There's less of a difference between inside and outside as all this sodium rushes in. Then this is the inactivation of the voltage gated channel. So this voltage gated channel gets inactivated because it becomes too positive. Then you get repolarization. As the potassium channels are open, potassium is higher on the inside, so the potassium starts to leave. That leaving makes it more polar because the inside is becoming more negative. Outside stays the same, pretty much the same positive. So because there's a bigger difference now, it becomes more and more negative, and you go down even below -70. At which point the potassium channels close, and you get more and more. The sodium potassium pump reestablishes equilibrium, and then you're back to start. You're back to rest. So resting, deep threshold is reached, depolarization, inactivation, repolarization, potassium channels close, go back up to equilibrium. And that just keeps going over and over again. This is what's called an action potential. So you watch this video, okay? You can either click on it, and I'll post the PDF online as soon as I'm done with this video. watch this video, go over these notes. Your quiz will be on Monday, obviously, since today is just Thursday is just no way I can make this happen. So Monday is going to be hopefully we'll all get back to normal. Remember the new policy. I'm going to give you a couple chances, but if once you're 2 chances, I'll have it all written up. But if you're late to class, you're going to have a consequence. If you're late to class without a pass, there has to be a consequence. That consequence is you're going to lose a bell work, and you can't get those points back. Okay, so don't be late to class without a pass. And I'm not sending you out to get one, so don't forget it. Not to mention two or more times, and you're going to get a detention. All right, that's it. Have a good one.